So welcome to the second day of the Monte Carlo tutorials. We heard yesterday by Stefan Pretzel about Pythia 8, and today we will hear by Christian Bierlich on Monte Carlo data comparisons using Rivet. Some organizational comments. All the software and settings presented here will be made available in the EIC software. The tutorials are also being recorded and will be made available on the YouTube channel of the EIC user group. Yesterday, we missed part of the tutorial, we missed part of the recording, and so we have the recording so far only up on the Indico page. We will record the missing part. It's from 37 minutes to 52 minutes, and then put the full recording up on the YouTube channel. The motivation of our tutorials is that for the EIC we have unique Monte Carlo requirements. Generators for polarized protons, but also polarized light ion processes. We need Monte Carlo event generators for electron ion, and our precision physics requires a really very detailed understanding of the merging of QED and QCD effects. So therefore we have teamed up with the international Monte Carlo community, who really has learned a lot in the last 2 decades of LHC physics, and one of the lessons learned there is that high precision QPD measurements really require high precision Monte Carlo event generators. This is available at LHC for LHC physics, and it's also clear that one of the lessons learned that Monte Carlo is not just some tuning, but it really encodes a lot of physics. So we are excited to work with the international Monte Carlo community, and today we welcome as tutor Christian Bierlich from Lund University. Christian is known for the Angantyr project, that is heavy ion in Pythia, with some very interesting work and some very interesting models. As part of his work, Christian has also really a lot of the existing results on heavy ion into the Rivet tool for Monte Carlo data comparison. And what this is exactly and how to use that, he will tell us today in the tutorial. So thank you so much for the tutorial, and we are excited to listen to you for the next 2 hours, Christian.
Thank you very much, Marcus, both for the introduction and for setting up these tutorials. Now I will see if I can share some slides. I can. Very good. So as Marcus said, I will be introducing Rivet. There will be a bit of me talking, and there will also be, hopefully, a lot of you working. Since we are no more than 10-15 people in the room, I would appreciate if you have any immediate questions. If anything is unclear, then please just try and ask them, because it's very difficult for me to see chat messages. If you have some technical question underway, if you cannot get the container to work or so on, try to write it in the chat first, then maybe someone can help you before I get to it. So yesterday, Stefan took you through an introduction to Pythia 8, and he even ended up running a Rivet analysis together with you, such that you could see Pythia 8 Monte Carlo compared to H1 data. Today, I will give you a somewhat more detailed introduction to Rivet. I'm assuming that you have a working installation of the tutorial image and Docker. If you don't have it, now is the time to do Docker pull, following the instructions on Indico, as well as a HepMC EP sample, which is equivalent to whatever you generated yesterday, which should still be stored on your computer. If you are a newcomer, don't despair, you can download it later. So the program is me talking for roughly 20-25 minutes with some introduction to what Rivet is. We will have some time for questions and to start the first group work. And then it's time for you to write your own Rivet analysis. We will do a bit of a follow-up on that exercise and start the next one where you will be introduced to some more advanced analysis features that you can put into your analysis. And yeah, then we will end. So the tutorial I'm giving today, I have taken the liberty to also write it up as in lecture note style. You can find it attached in the Indico program, as well as these slides. This can be a good aid together with the YouTube video or whatever I'm saying. It should allow you to kind of go back and reiterate what I have already been saying. So what is Rivet? It's an analysis system which allows you to fast extraction of observables from any Monte Carlo event generator, which is compatible with the HepMC event output. So as an analysis system, it is not much different from what you probably already know. Maybe you're using Brute, maybe you're using some standalone analysis tool, maybe you're using something else if you are already in the habit of analyzing Monte Carlo events. What sets Rivet apart from the rest is that Rivet is very well suited for Monte Carlo versus data comparisons. And since it is very well suited for this, there are already many analyses implemented into Rivet. So these are data analyses done by several experiments. So there's a breakdown chart down here from different experiments, which is kind of the analysis we want and the analysis we already have in green. What you can take from this is that at the time of writing, which was yesterday, I guess, there were 917 analyses implemented, spanning basically all colliding systems. There are E+ and minus analyses dating back from the lab days and before. There are a lot of, there are some old SPS analyses, there are analyses from RIC and Tevatron made available, and there are quite a few LHC analyses, in particular, as you will see, Atlas analyses. That is simply due to the fact that a lot of the original Rivet authors were Atlas members, and Atlas thus have had a bit of a preference. So aside from being a data analysis tool where you can implement some analysis, it is also, in fact, the tool of choice for communication between Monte Carlo developers internally. Say I want to communicate with Stefan about some new observable, something we could do, and we would perhaps want to involve a Hervik developer, then we need some kind of language to define this observable. Rivet is very well suited for this. It is also very well suited to do the same kind of communication with experiments. Say I have a prediction for some observable, then I can make an unambiguous message about how this observable should be defined. So one of the main things is that Rivet by design prevents you from looking at unphysical observables. If you have never encountered this term before, I will try to explain it. You may remember the event graph of an EP event from yesterday. I've put it in the background here. And as you may remember, there were a lot of particles, a lot of intermediate states, and a lot of places where different event generators could do things differently. But at the end of the day, we get some final state hadrons, which are hopefully more or less equivalent to what an experiment would measure. If I want to compare something across Monte Carlo event generators and compare it to an experiment, this is really the level I need to make a comparison on. This is not always the case when you sit down and read, say, an experimental paper, because you will have experiments who have tried to unfold the data down to something which is not uniquely defined, but is only defined in terms of some particular model. So as an example, you have many Hera analyses which are corrected to a Born level, meaning that they have used some simulation to unfold their data down to some Born level observable. This may be all well and good when you sit down and write the paper, but when someone comes back 10 years later and don't necessarily have access to the same simulation as they had at the time, it can be very difficult to actually use that data for anything useful today. You have even some steps which cannot be compared across generators because models make different choices. Now, on top of these kind of general observations, you have some further complications added by DIS physics. So you have the problem that in DIS physics, you have a scattered lepton, and that scattered lepton is not necessarily equivalent. So the Q square you get from a scattered lepton may not be equivalent to the Q square you use to set up your calculation. So Stefan showed this very nicely in an example yesterday, because the experiment needs some experimental definition of the scattered lepton, whereas in a theoretical calculation, you can just say, well, I know what the scattered lepton is because I put it in there in my calculation. And that is a fundamental difference you need to address. And you have a similar problem if you try to define diffraction in DIS. So does heavy ion physics. And since the electron-ion collider would be a nice combination between DIS physics and heavy ion physics, we will probably encounter some of the same problems. One problem of particular note is measured centrality versus theoretical centrality in an AA collision. This is something we will address in these tutorials. And also jet definitions. You have experimental jet definitions through some jet algorithm versus some maybe a pattern level jet, which may or may not be defined in the same way. The takeaway point from all this is that Rivet is designed to mitigate. So if you write down an analysis in Rivet, you will have access only to the same thing as the experiment has access to. So if you cannot put your observable or your analysis into Rivet, there's a fair chance that it's not physical. I also want to come back to this point I made before, Rivet as a tool of communication. So as I said, a very frequent use case for us is not just comparing Monte Carlo to data, but to compare observables across generators for prediction or validation. So there are two key features you can have in mind here. So first of all, the fact that I can write an analysis which I can apply to any Monte Carlo event generator which uses HepNC events means that I have a very rapid turnaround because I can write down an analysis, pipe Pythia events through it, and then I can send it to my colleague in Herwig or Sherpa, and they can pipe events through it as well. And we know that there will be no fundamental differences between the analyses as applied. And secondly, as I said before, the observables we try to define are physical by design. It's also useful not just for comparison between Monte Carlo and existing data, but also between Monte Carlo authors and experimentalists who want to take data in the future as EIC. So you can easily set up some ideal detector with some acceptance, and you can set up the trigger definitions. And this means that if you just implement this in a Rivet analysis, which is basically a 1 or 2 liner, there's no need to ask any MC developer to install some large experimental code base in order for them to run your code. And also, again, there's no ambiguity in the definitions of observables. For this reason, the most Monte Carlo authors actually prefer using Rivet analyses when communicating with, say, an experimentalist who writes me saying, Pythia does a weird thing for this observable. Can you take a look at it? If you send me that request as a Rivet analysis, then I can sit down and I can run your analysis immediately, and I may or may not be able to figure out what is going on. If I need to compile your large code base dependent program, I will simply not get around to do it in any realistic way. So I can summarize this statement as I did at the bottom of the slide. If you do not use Rivet when communicating with Monte Carlo authors, you should expect long answer times. So let me start getting down to the details of Rivet. It is more or less an analysis framework, as most of you probably know it. Once you start an analysis, you have to initialize it. There's a C++ class, which is called analysis class. You will write your own analysis class, which derives from this. When you initialize, you will book objects. This means that you will define whatever histograms you want to fill, and you will declare something which is called projections, which we will get back to. You can think of them now as just the collections of particles you want to look at in every event. Then you go to the event loop, and for each event, you call a method analyze, where you will project out all your projections, meaning that you will get access to the particles you want to look at. You will construct your observables, and you will fill histograms. You go on and on and on until there are no more events. And then finally, you will run a finalize, where you will normalize histograms, you will construct ratios, you will do all event averages and so on, and then you will output some results. So let's take a closer look at one of the analyses you ran yesterday. And instead of me having pasted it all into the slide, I will actually ask you to go together with me to the Rivet documentation. I'll just exit these slides, and on your own machine, you should be able to just click this link in the slides, which will take you to the Rivet documentation. So do you see my web browser, anyone?
Yeah, we can see it.
Very good. So this is one of the analyses you ran yesterday called MCDIS Check, which is a very simple DIS analysis, which is made in more or less the same way as I indicated before. So first of all, you define your analysis. So you make a class which derives from the analysis base class. Then you have a macro which defines a constructor. Then you have the init method where you will book these projections, and you will book histograms. Then the analyze step, which is called once per event. So you see the event is an argument here. You apply these projections. You get your relevant quantities. You fill histograms. And then finally, in finalize, you normalize your histograms. And of course, you need to make sure that your histograms are declared as members of this class in order to have access to them across all these methods. So let me just get back to this concept of a projection, because this is very central to Rivet, and I want to do it here because I have a concrete example. Whenever you do an analysis of Monte Carlo events, you need access to, say, a number of particles, or you may need access to some reconstructed kinematics quantity. You may need access to something else you can calculate from an event, say all the jets in an event or something similar to that. Now, in this case, the central projection is this one here, DIS kinematics. The DIS kinematics, and you will study it further in further detail in the group session later, is a projection which projects out the DIS kinematics quantities, so DIS x, y, and q squared. And the crucial point here is that it will do it in the same way as you would do it in an experiment, meaning that you need some kind of definition for what is the DIS lepton in this event. So the default setting of DIS kinematics is to take simply the hardest lepton in the event. And there are a couple of other choices which you can study later. So,
Christian,
yes?
There was just a comment by Kolja in the chat. If you could make your fonts larger or just zoom in, it would be easier to read. Perfect, thank you.
Good. I would also suggest you to actually open this web page on your own computer in addition to looking at mine, because you will be using the documentation.
Sure, but it's just difficult to go back and forth, and it's nice to look at your screen and actually be able to see what you're highlighting.
Of course. Is this better, Kolja?
Much better.
Okay, very good. So the default setting here for DIS kinematics is to use the leading lepton, and then q square will be reconstructed for that. That might not be the real q square used in the calculation, but it's the best we can do, and it's equivalent to what the experiment did, and that is the important thing. Good. Let me go back to, I think I went through booking histograms, projections, class structure. Oh, I should mention, yes. The histograms here, as you see them, they are filled with the relevant quantity. So Stefan discussed event weights a bit yesterday, and users of previous versions of Rivet may want to ask, where is the event weight? From Rivet version 3 and on, you don't need to worry about filling the event weight together with the kinematics quantity. Rivet will take care of that automatically. So basically, if you were worried about event weights previously, the message is don't. Once you've run an analysis, you will get some analysis output, and you will be running this analysis from command line in a minute. The output file is in a histogram format called Yoda. So you can click the link here to go to the Yoda documentation, which I will not do, but feel free to do it yourself. What you should know at this point is that Yoda is a lightweight histogramming package, and it's optimized for heavy usage, meaning that by default, you will store all second order moments of all histograms, meaning that you can reconstruct all relevant statistical quantities that you would like. Now, the frequently asked question at this point is, but root, what about root? And just to preempt this question, root is a bit too heavyweight for us to include as a dependency for a quite lightweight tool such as Rivet. It simply doesn't make sense to include a dependency which is so many times larger than what you would use it for, i.e. Rivet. But if you like root, and if you would like root histograms in place of your Yoda histograms, you can convert them. There's a tool, Yoda to root, included with Yoda, which you can use for that, and you can study the online docs as linked above, if this is something you need. So, setting up Rivet. If the installation of Rivet follows kind of normal package installation, and if you want a local installation of Rivet at some point, it is mostly harmless. You can click this link and it will take you to an installation script, which you should be able to read through and run, and it will install Rivet and all dependencies on your system. It does require C++14. For this tutorial, however, we use the same Docker image as yesterday, such that we don't need to take up any of your time installing programs, and it has Rivet 3.12 installed already. So I'm assuming you have already done Docker pull, Electron Ion Collider, Pythia EIC tutorial. Now, instead of going into the Docker container as we did yesterday or using Jupyter notebooks, we will just stay on the host system. But what we'll do is to expose the 4 relevant Rivet commands that will be used today such that you can use them as if it is installed on your own system. Oops. So let me just show you how to do this. And please feel free to follow the instructions as I do it. Now is the time where we make a live demonstration, and this always goes wrong. I have here a terminal, so I have navigated to the same tutorial directory as we used yesterday together with Stefan. I can do ls here, and I can see that I have some of the files, so the notebooks file, the notebooks folder that was in use yesterday, okay? So if you paste this full command, it will expose Rivet from inside the Docker container, mounting current directory as the working directory and setting appropriate user ID and so on. I just copy the whole thing, and you can copy the whole thing here, paste it. Let's just do the same, all 4. So now you should be able to run Rivet from the command line as if it was installed in your own machine. What you can try to do is to just do Rivet -- help, and you will see the Rivet help menu come out, which gives you a bit of an idea about what kind of options you can give to the Rivet command. And you can do Rivet -- list analyses, which will give you a very long list of all the analyses currently available on your system. See, there are a lot here. So if your system does this now, you're good. And I will now take you through the first part of the exercise, and the rest you will do yourself, because it is time to get to work. So I will show you how to run analyses from the command line. So equivalently to what you did in the Jupyter notebook yesterday, you will now just be doing it on the command line using your pre-generated HepMC file. So I will follow the tutorial sheet, which I uploaded to the Indigo page, which you see here. Should go to section 4. And I will simply follow this step by step. So if you don't have a HepMC sample on your system, you can just wget this one. This is a sample equivalent to some of those you made yesterday, and run on that. So we have already done Rivet -- help and Rivet -- list analyses. So now we will simply run it, and you can just copy from here, and you call the command Rivet, you tell it what events it should look at, and then you can give it a list of analyses, prefacing each analysis name by -a. So we want to run these 2 analyses minus MCDIS Check, which we looked at before, and this H1 analysis looking at energy flow. And off it goes. You see that it gives some information in the beginning. First, it tries to figure out what kind of file am I looking at. And finally, it figures out that it is a gzip compressed HepMC event file, and then it gets to work. So one good thing, one good feature of these projections that I told you about before is that when you run a lot of analyses at once, at the same time, this projection system will actually unfold all projections onto each other such that you will make, in essence, just the number of event loops you need. So you don't serialize all the event loops, but you will actually parallelize them as much as you can. This is a quite nice feature. It means that it doesn't take up an infinite amount of time to run a lot of analyses. So I think that the video system is putting up.
Question?
Yes.
So these alias commands which you defined, I think they work beautifully on Linux, but there might be some problems on other operating systems. So maybe a simple way to, as an alternative, is just to execute the command with docker run -rm -it and then bash at the end, and then one can run all of these commands directly in the Docker container. It's of course not as convenient as the aliases, but it might help with following the steps.
Yeah, unfortunately, I am not too familiar with Docker on Mac. It should work, but there might be a problem that some of the characters are funny or something like that. I would guess that is the most probable issue. If there are any Mac expert, I would be happy to hear from them, because I have not owned a Mac for many years.
I think it's just a difference in shell, but simplifying it will make it shortly work as a workaround.
Good. So now you see the analysis are finished, and it comes with some more messages. So this MCDIS check is not validated. This refers to the fact that ideally all analyses coming from experiments should be properly vetted and validated by the experiment to confirm that the Rivet analysis in fact does the same thing as the experiment. Sorry, is that a question? Tyrone, is that a question? I guess it was not a question. Then I will kindly ask you to mute. You have already done that. Very good. So all analyses should be vetted and validated by the experiment to actually confirm that they are doing the same thing. Now they have run, so we can just go ahead and plot it using the Rivet make HTML script. And it will plot whatever is produced by the analysis in this Yoda file. And again, I encourage you to just follow the instructions on your own computer. Good. And then you can take your favorite web browser. I usually use Firefox, and open index.html inside Rivet, the Rivet plots directory, which have been generated by Rivet make HTML. And what you will see here are the figures from the two analyses with links to the Inspire and the HEP data reference. And in here, you actually see how this Monte Carlo we just generated compares to the experimental data. So far, so good. Go back to the index. We can study MCDIS check. And so we can clearly see that there was some Q-square cutoff somewhere here. I think that it is somewhat lower in this MC sample than what Stefan showed you yesterday. which is why you don't see the same type of effect, but that is all well and good. So coming back to the game plan here, you will be divided into breakout groups, and you should follow the tutorial sheet, which I just showed you, basically picking up where I stopped. You will study the source code of the two analyses you just ran, and you will start writing your own analysis, which adds some more observables, and it will take you through it. You should work through until section 7, or however far you get before that, and when we come back, we will go on to more advanced analysis techniques. So while we work, I will visit all the breakout rooms and I will answer questions that you may have. And you will be given 35 minutes into this initial task. And if you need a short bathroom break or something similar, please take it during the 35 minutes. But before I start the groups, I want to take the opportunity to ask if anyone has any questions at this point, because I have not been able to follow the chat.
Hi, Christian. Sadhna here.
Hello.
Hello. So when we write the analysis code, we should give it a new name, or we just modify in the existing
So I'm assuming you have gotten started. So the tutorial sheet you follow will give you all instructions as to what you should do for the tutorials. So I was more thinking if anyone has a more general Rivet question. It seems not. Then we can also get back to that later. So I will. So just to answer your question in good order, when you make your new analysis, you will use the script Rivet MK analysis, and you will give it a somewhat different name. I have chosen the name MCDIS mod for a modified here, but you can of course choose any name you want. Okay, so I will stop sharing, and then I will see if I can figure out the breakout rooms. Sign. So I will assign, so there are 11 participants minus, so I will assign you into 2 rooms. Let's try to do that. So welcome back. think we are more or less here. So I hope that you all got a chance to take a look at the analysis code and possibly make some modifications to it. So we will now just briefly follow up, and instead of me just showing off, I would rather ask if any of you would like to show some of the code you wrote. It doesn't have to be complete, it doesn't have to be perfect, but I know that at least a couple of you may have gotten some way through the exercise. Any volunteers?
Maybe just ask the two groups explicitly.
I mean, I don't want to be the teacher's pet. I think it would be more useful if somebody else.
What did you say, Cole? You don't want to be the teacher's pet?
Yeah, that's right.
Okay.
But I mean, I can do it, of course.
Yeah,
Please do. Please just go ahead, and if anyone sees something that they got a bit differently or have a question, please just shout.
So, I mean, this is literally just almost copy paste bits by bits from the tutorial. I didn't do a whole lot of things here yet because I ran into the issues with compilation at first. Well, because I made one mistake. So there's one typo actually in the tutorial. There's this guy missing.
Ooh. Thank you for catching that.
Oh, it was easy enough to catch. It's through errors. So then it does relatively simple things. It projects onto the final states. Then I think was this H1? So it separates between the two X regions, and then runs over the particles. In this case, we only want charged hadrons. What is a hadron in this sense? Is it the physical definition of a hadron? Because there are plenty of people who will consider an electron a hadron.
An electron is not considered a hadron here. It is so the definition of a hadron is whatever DISFS thinks. So DISFS will give you a list of particles, and then you are asking each of those particles, are you a hadron? And it means, are you a composite particle made of quarks?
And does it use its own library for particle information, or does it install, for example, Pythia, particle PDG information?
No, it uses its own.
Well, the IDs are PDG IDs.
Yeah, the IDs are PDG, but it uses its own implementation of the same logic as you will find in Pythia or whatever to differentiate between hadrons and say leptons. But a lepton will not be considered a hadron, no.
No, but I mean, let's say I want to look at mass of some quirkier new particles. There's often some difference in opinion about what the mass is of a particular particle, and depending on what PDG version you're using. Root also has some static version of an old database. So they also bring their own.
I'm sorry, I missed the last part, Kolya.
Don't worry about it. So what would you like me to do?
So you have done what I wanted you to do, basically just showing that these are the steps required. You book some new histograms, and then and this is all well and good. So maybe what I will do is just to steal the screen share. and show essentially the same thing as Kolja was just showing, where there are a couple of important things to keep in mind. So first of all, you were filling a histogram with W squared, which you can just get from, that was up here, which you can just get from the projection. And then when you fill histograms with particles as a function of eta, the reason I split into two X regions was actually not to follow a certain experiment, but it was to show that then you need to make a counter for each of these X regions to make the correct per event normalization for these two regions, as I think you also did. Then you had to add in a loop over all the particles in your projection. You have to apply cuts, and you have to fill the histograms, and finally you have to, in finalized scale, the histograms. You will build the analysis and run it, and finally plot it. And once you have reached that point, you have basically made your own first Rivet analysis. Now, if any of you did not get that far, which I know for a fact is the case, then you can take a look in Appendix A of the tutorial sheet, where I have pasted a solution to the analysis which was asked for here. Now let me see if I have the same. No, here there. So the missing column that Kolja was referring to has been included here. Good. So are there any questions from you guys to this part?
So maybe one, from my side, which is since I'm kind of an old school Rivet user, I wasn't aware of these counters and how they actually work and that they keep track of different things. What things do these counters keep track of? Meaning, kind of, I saw that there's a sum of weights, I guess.
Yes, excellent question. So a counter is basically just a glorified double. The thing is, let me just open up MC, no. The thing is, I want to be able to do several things. First of all, when I count the sum of weights, I would like actually the event weights to be counted, should there be event weights. Now, since I am not using event weights normally in a Rivet analysis, so as I said, you don't use event weights when filling histograms, you should also really not use it when filling a counter. Doing fill on a counter will do the same type of fill on the counter, just with as when you fill a histogram. So it will keep track of the events automatically, of the event weights automatically. Secondly, you often want to take your Rivet analysis and then parallelize the running of it. Say you want to run 1 billion events through, or say you want to run over heavy ion events with 10,000 tracks in each event. Then you want to parallelize such that you run maybe 100 times and then have 100 Yoda files which you have to merge afterwards. If you want to do that and you want to do it in a statistically reasonable way, sometimes you actually would have to run finalize again over the merged sample, and then you need access to the sum of weight counters. If you use counter pointers, maybe there's nothing here, shame, in this Rivet file, then they will be streamed because they are a proper Yoda type, and they will be streamed to the Yoda file such that Rivet can take good care of everything. Was that answer to your question?
Yeah. No, that's kind of, I see the usefulness. kind of neat.
Yeah, of course, if you're used to using doubles, it can be a bit cumbersome to change, but the benefit outweighs the trouble, I think.
So what if I don't like Yoda? Is there like a root version of this?
There's not a root version of this, but there's a script called Yoda to root, where you can convert your Yoda histogram to root histogram. So you just get a T tree of histograms. And don't ask me any more detailed root questions than that, because that is
Okay.
about as deep as my root knowledge goes.
Worries. But one more question I do have. These files are just like HepMC, they're very large and wasteful because they're ASCII. Can you automatically produce zipped output?
You cannot automatically produce zipped output, but we are currently looking into using HDF5 binary files instead.
Yeah.
So you would have that as an option.
And yeah, that would really be excellent.
So the motivation for using Yoda, one of the motivations for writing Yoda the way it is that it is nice to have a human readable format, or it can be nice at least. Now, with more and more stuff being put into these Yoda files, when people do, say, automatic variations on them on the Carlo or things like that, these Yoda files tend to grow, making them actually less human readable because they are so large. So we are currently discussing if the benefits of having a human readable file format is dwindling. And there are people actively working on making a neater option for this.
But why don't you actually just gzip the Yoda file? Because with zless, you can still read it easily and you compress it by a factor of probably 7 or so.
Yeah, that would probably be possible because there's, I will note that down. I think the honest answer is that it has never come up as a problem.
I mean, I found it very easy because chances are you're using an OF stream at some point just to write this out, and you just replace it with the GZ stream and you're good to go.
Yeah, and all the linking has already happened. So I have not noted that down, and I will put it in as an issue if it's not already there. Thank you for that comment.
You can steal the streams.h from Pythia or Sherpa, which are identical, to do that.
Yeah. So let me move on to the next part, which is the possibility to add an advanced analysis feature to your analysis. So I have put in a selection of 3 advanced features, and you can choose between them, and you can either implement 0, 1, 2, or 3 into your analysis. I would recommend that you get to the point of having the full modified analysis doing these 2 DN-DETA histograms first. So the first option is to add the possibility to interact with the analysis using so-called analysis options on the command line. The idea is that when you run an analysis on the command line, Rivet, MCDIS, whatever, I have my HepMC file, then instead of just writing something like this, I want to be able to pass it an argument. Say I have an option in the analysis as it is given in the tutorial PDF, where I will select between 2 different boost systems. So I will change from the hadronic center of mass to the bright frame. And this I can then pass as an option here. So with the stuff that is implemented, I would write, say, boost equals to bright, and I would change the behavior of the analysis. The second thing you can do is to add percentile binning observables. This is something which is very often used in heavy ion analyses, where you have centrality binned observables. So the idea is you have one observable and then you bin that in percentiles of another observable. So this requires you to make a calibration run where you output a calibration histogram, which you will then read in the subsequent run and actually use what you generated in the first run to calculate the binning in the second run. That's the second possibility. The third possibility is to use FastJet, which is the very well-known library for finding jets, and simply implementing, I think it's a KT jet finder, and plotting the jet multiplicity and the jet ET, I think it was, and plot those in histograms. And you can find the instructions for all three in section 7, and we will just proceed as we did before, and you will just see how far you come. And then 5 minutes to 6, I will call you all back into plenary, and we will finish the tutorial for the day. Is anyone unsure what this final part of the exercise is about?
One question, Christian, as we are only 8 participants left, should we just be here in the breakout?
Yeah, then we will just stay here, and there's no need to go to a breakout room. I didn't see that there were people dropping. Then I will not send you to breakout rooms, but feel free to just start working away and just speak up if you have any questions while you work, and we will answer them. So, thank you to those who have been hanging on until the bitter end. And if you have followed the tutorial so far, you can now write a Rivet analysis, you can run it, and you can produce figures. I hope I have convinced you, also on YouTube, that Rivet is the most useful tool to preserve existing analyses and to aid your communication with Monte Carlo authors. There's, of course, a lot more functionality in Rivet than what I have introduced here today. There's functionality for detector simulation. There's a lot of multi-weight and a low counter event functionality in there. And there's even more functionality for heavy ion analyses than what I've already introduced.
Christian?
Yes?
You're not sharing at the moment, I think. So if you wanted to share your slide, that could be, maybe you should start now.
Yes, here we are. So the slide just states what I already said. And I got some more functionality, including the heavy ion stuff. If you need more, there's extensive documentation on the Rivet website. You can write the Rivet mailing list. And if you want to contribute, if you're an experimentalist, you can implement your own analysis. If you're a phenomenologist, you can make your generator Hep and C compatible such that you can also use Rivet. And finally, of course, if you want a similar tutorial at your lab or your university, please feel free to get in touch. We can also do a different flavor than EIC, for example, something with focus on heavy ion or focus on jet physics or something else. And as always, feedback and questions are most welcome. And thank you very much for your attention.
Thank you very much, Christian, for the tutorial. This was very, very helpful to really get started with Rivet.